Hello class, this is Professor Coles. I'm going to give a brief overview of Xfoil, which you'll be using for your homework and for the midterm projects. Xfoil, I'll have the link up to the page. This is the web page where you'll get the executables. It's a two-dimensional flow solver for airfoils. Very well known, probably the best regarded foil software out there, and has been for about 25 years. It was written by Mark Drella. One of Drella's big contributions to designing airfoils in general is he worked on inverse methods that allowed people to set a pressure distribution, a desired pressure distribution, and it would calculate the foil shape needed to do that. And that's what they call an inverse method, inverse airfoil design. Now, the executables are down here. Software, I realize this page looks like it's also from the early days of the web, but I assure you the software is quite good. So for Mac stuff, you click here. Actually, I think I went with this one, this third-party software here, which takes you to a link, and I think it was a regular DMG that I installed on my machine. You will need, if you're running on the Mac, the graphics are done through X11, so you'll need Quartz, QUARTZ Quartz on your machine. That's a freeware. You may have already installed that anyway. And then the executables in the MNE 490 lab, I used this one and it worked fine. Xfoil 6999 zip. If you're in the MNE the MNE lab, computing lab, just save that into your into your Z drive, where you will be allowed to download and install it. It's an executable and some extra files. And once it's in there, or once you've installed it, you can go ahead and run it. I can't remember where mine got installed, so I'm going to find it. Here it is. Okay. I'm going to run Xfoil. Okay, so Xfoil is a terminal-based program. Of course, you can always save your string of commands and rerun your input deck if you want, but there's no GUI interface. It's all done by hand. So it takes a little getting used to. There is a manual which I'll put a link up to as well. We'll only be using a real subset of all the potential commands. We're not going to do any inverse modeling, for example, which is a little bit more complex, and we're going to use standard stock airfoils, so we won't have to load in airfoil coordinates. So you can read in your own coordinates if you want, if you have some design, or choose from a list of standard systematic series. In our case, we'll work with the NACA 4-digit series. You can see up here the options. So the prompt is here. I'm at the highest level, which says Xfoil here. We'll be going into the submenus in a second to set the flow conditions for the solution. I think what I'll do is I'll try to run through. Well, I'll just do a basic simulation, then I'll go back and do a polar plot, meaning a range of angles of attack. Sometimes I get a little caught in these menus and I end up quitting and restarting. So don't mind if I do that. I haven't used this for quite some time, so I'm trying to, my brain is trying to remember. So first I'm going to set the foil, NACA 2412. So I can write this in one line, or I can just type NACA and it'll prompt me to say which one I want, 2412. So that's the 2% camber, 40% back on a 12% thick foil that we worked with from the Cessna airplane. It's been used actually on other planes as well. And I'll hit return, and it gives me some information. Tells me the max thickness is, the max camber. There it is. It's close to 0.4. These are all parameters for the computational scheme. It's a panel method, so it's distributing source and vortices along the airfoil, and it's using, it looks like 160 of these along the chord. And you can affect these things, but whatever would have been selected already for the standard defaults, with the exception of one parameter, which we'll show you in a second, are good enough for solving our situation. So you don't have to touch any of those. So now we have the airfoil set. Now I'm going to set the operating conditions. So you go to Oper. So now we're in a sub-menu of Xfoil. I can always go back up by hitting return. I just hit enter, and now I'm back in my Xfoil menu. I'll go back in Opera, and any of these menus you can hit, including the sub-menu here, I can hit question mark, and it gives me the list of options. There's quite a few. We'll probably use a tenth of these tops. the first thing I'm going to do is change the Reynolds number. This flow solver can solve for inviscid flow and viscous flow. We're going to focus on viscous flow. So I'm going to, right now it's toggled off. You can see the option here. I'm going to toggle it on, and I'm going to set the Reynolds number in the same line. So I'm going to say visc 1, let's call it 5e to the 6. How's that? 5 million. Okay. M right there is Mach number, which will be 0. We'll assume this is subsonic flow. And what else do I want to do? The only other thing I like to do is there's a viscous solution iteration limit. Sometimes the solver at high angles of attack and perhaps higher Reynolds number fails to converge. It will tell you I didn't converge, hit exclamation mark to keep going, and you're welcome to hit exclamation mark, enter, and it will keep trying. But in today's computers, there's really no reason not to set a pretty high limit here. So this is number of iterations. It normally stops at 10. Let's just make it 100. That'll be very fast anyway, at least on our modern machines. And then what I'm going to do is set the angle of attack. So let's put alpha to, I don't know, 3 degrees. Alpha 3. And it should bring up a plot. It might take a second this first time. Solving. Opening my X windows. On your Windows machine, it will immediately plot it. Here it opened quartz, X11 through quartz. So you see the inviscid, white line, and viscous solutions. You can see transition occurring here. This is a little jog in the CP curve due to transition. And this shows you the airfoil. So effectively it displaces out the airfoil due to the thickness of the boundary layer, which influences the pressure distribution here. So the actual thickness, the fact that the boundary layer itself has thickness to it, changes the apparent shape of the airfoil to the free stream flow and influences the pressure distribution a little bit. We could rerun this if we wanted to as an inviscid foil and see how much different the lift is at this given angle of attack, and that might be an interesting exercise, but we'll skip that for now. So over here is report 5 million, 3 degrees, your CL is 0.5790. The CM, this is the moment coefficient. And given that's negative, I'm guessing it's around the quarter chord, although we'll have to check that. And we have CD, that's the drag coefficient, and that includes both viscous and pressure components to the drag. So that's the total drag on this section, and then gives you your L over D for the section, and N crit has to do with the turbulence level, and we can adjust that in a second. But you can see the transitions occurring here, the typical suction peak towards the leading edge. This is the bottom surface pressure coefficients. The pressure coefficients, again, they're upside down, so more positive here, negative here. Pressure coefficient of 1 is the stagnation point right here. Pressure coefficient of 0 is free stream flow. So on the upper surface, it's back to free stream velocity around here, and it's back to free stream velocity in the lower surface, almost along this entire section. It's near free stream velocity. And then we have some, let's see, deceleration starting here, even on the upper surface. The pressure gradient is adverse, and it's decelerating all the way to the trailing edge. And on the lower surface, it's decelerating from about here. The pressure coefficients are getting more positive here until we match the pressure condition on the trailing edge. And you can see the differences that occur, particularly at the trailing edge, because you have a small wake here. It's hard to predict that, but there's a small wake here. The airfoil is not shown at an angle of attack. Even if we increase the angle of attack, the airfoil itself will still look like this, but the pressure distribution will change. And let's go ahead and do that. So I'm going to put alpha to, let me make this window a little smaller, so hopefully it will just refresh this and you can see both. Hello, let's go. My screen captures on, it slows everything down. Alpha, what did we have alpha before? It was at 3. So let's put this actually at -2 and see if we can get this pretty close to 0 lift. So we're at -2. Where are we over here with lift? CL's 0.015. Yeah, that's pretty small. It's going to be small enough. So you can see that because it's not a symmetric foil, the upper surface, which is blue, the upper surface pressure distribution and lower surface pressure distribution are different. But in fact, if you integrate the difference between them all the way down, it cancels out to 0. So here we actually have some suction on the leading part of the lower surface is actually producing suction or a downforce, which is eventually canceled by the upper surface towards the trailing edge here. So there'll be a moment involved, actually about the same size, 0.05. So it's not symmetrical pressure distribution, but it does cancel out to produce zero lift. And we can go to a high lift. If we want, we'll just go to alpha, I don't know, put it at 6 degrees. At some point it may not converge. Let's try 6. That work? Alpha 6. There it goes. I'm not sure what just happened there. Alpha 6, so you can see the very high suction peak that's occurring, a strong adverse pressure gradient. Let's just really test this routine, because I'm getting a little suspicious here. Let's put it to 10 degrees, and it still finds a solution, so we may not be able to actually detect separation with this. I will look into that. Right, so these are getting to unrealistically high angles of attack, perhaps. So what we'll do is we'll look at the polar plots. You can start to see it's predicting some kind of separation here. Let me back this up to alpha 15. So we're getting some strong separation in the trailing edge here, a wake associated with this. So keep in mind this airfoil is actually at an angle of attack, a fairly steep angle of attack, 15. Let's put it back to 20, and there's your separation zone. Our CD's gone up quite a bit, and then we're going back to 25. And now we have a very large drag coefficient. So it's totally separated at this point, but it does still seem to be converging, which is surprisingly. So I don't know quite how it predicts this, because this is truly unsteady flow. So I don't know exactly how this flow solver works or how dependable it is once you have large regions of separation, but it probably does predict well when separation is occurring. So let's go back to a non-separated angle of attack, went back to 10 degrees. Now what I can do is, so you can save these plots, you can take screenshots, you have the data over here. Now if I want the data over a large range of alpha for a given Reynolds number, I can do what's called a polar plot. Give me a second to remember how to do this. So I'll go back to my question mark menu. Now to switch from the CP plot we're on now, CP of X, to a polar plot, you use the seek P option, seek P. And now I'm going to start a polar, and then I do that with PACC. I'll go auto point accumulation active polar. That's quite a mouthful. PACC, and now I'm going to start the polar. Okay, and ask me, do I want to save it in the file name? And we'll save. I'm going to call it 2412 screen cap. And this is polar dump file name. I'm not sure what that means and how that's different than save file name. We're going to skip it. Now, polar accumulation enabled. Now what I'm going to do is put, instead of a single alpha, I'm going to put a range of alpha. So I'm going to seek a sequence of alpha from -2 until, say, 10 in increments of, actually, for fun, let's go to 25. I don't know what that's going to do, but we'll do it for fun. To 25 degrees in range of 20 degrees in range of 0.05. Let's make it 0.1. So, no, make it 0.05. No, I'm going 1, sorry. 0.1 degrees. So now I'm going to hit return, and hopefully this will go. And go. Okay, so it's producing the polars here. It is climbing up. CL's climbing, CL's climbing, CL's climbing. Oh, you know what? The limit of my polar plot is 10. However, it apparently wants to plot right past that all the way. Now it's starting to bend over until you can see CL is stalling here. Now the problem is the limits of my plot are not working, so I'm going to have to figure out how to change that. I will figure that out for you. But that is a polar, and I can save this data. I'm trying to remember how I did that. So it says written to 2412 screen cap. I'm not sure what directory I'm in on my computer here. So let's just figure out where we are. Here it is, 2412 screen cap. Okay, so it saved it into this directory where I launched the executable. this is the polar, and what you're seeing here are all the predictions of Xfoil: angle of attack in degrees, lift coefficient, drag coefficient. This is the pressure. This is pressure drag only, which is good to have. So basically, this is the total drag, viscous and pressure. This is pressure drag only. So viscous, I should say. Let me be clear about this. This is the frictional drag from the boundary layer plus the viscous pressure drag. The drag that's when you integrate the pressure, and we've been calling it viscous pressure drag because it's due to the viscosity that we have separation, but it becomes ultimately from the pressure integral. That's here. It's small compared to the friction at low angles of attack, as we know. Moment coefficient, and these are the transition locations. On the top, it's transitioning about halfway down the foil, and on the bottom, it's transitioning about it's transitioning about 10% of the way down the foil. And let me actually see if I can keep this date open. I want to go back to my other plot. Let's see if I can do that and redo that. So let me go question mark. I'm going to go back to my CPX plot. I'm going to say seek P. Okay, I'm just going to do 1 alpha again, which is -2. Okay, so you can see when it is actually at -2 degrees, which is a zero lift configuration, or nearly so, that the strongest suction peak occurs on the lower surface because it's sort of, the foil is sort of bent down like this. Strongest suction peak or highest velocity is occurring right here. Excuse me. And so that's where this adverse pressure gradient kicks in. You have favorable pressure gradient, accelerating flow, adverse pressure gradient. So transition is delayed by favorable pressure gradient, and then the adverse pressure gradient is adversely affecting. It's causing transition or leading to transition. So it's at -2 degrees. You have nearly zero lift. Drag's all to do to boundary layer frictional drag or parasitic drag, and then we have on the bottom transitions happening about 15% back. Let's see where that is here. These are all 10%, so it's occurring about here. You can see the little wiggle right here in the CP curve associated with transition occurring right at 15% as it reported here. The transition in the upper surface is about 60%. Let's go back and figure out that is 1, 2, 3, 4, 5, 6, and you can see just a small wiggle. I don't know if this shows up in the video, hopefully it will, right here in the upper surface pressure. So there's a delayed transition on the upper surface, and it has to do with differences in pressure gradients. And this is, you can see how difficult it is in general to impose a transitional point at a given Reynolds number. On a flat plate, you can pick numbers, and those would be more related to free stream turbulence and roughness of the plate. In the case of an airfoil, because you have favorable and adverse pressure gradients, transition is delayed by favorable pressure gradients. That's why foils like the is it the 66 series or 64 series NACA foils have long kind of slowly sloping sections, so they don't get into an adverse pressure gradient until further back. They try to keep it laminar as far back as possible. So here, in this particular state, angle of attack, it is laminar on the top surface. Even at a Reynolds number of 5 million, it's laminar halfway back. You're getting to almost 2.5 million here because it's favorable for so long. It's a favorable pressure gradient all the way about here. So you're really not starting to mark the potential for transition until here. So these codes this code kind of predicts the point of transition. There's definitely empirical models to do that. And one key thing that depends on is the level of free stream turbulence. So this Xfoil assumes some default level of free stream turbulence. I think it's probably in the fluctuation velocities. You could change that or modify that. I wouldn't suggest doing that here because we don't have any justification for doing so. Let me just put it at a higher alpha, say 2, so it's in a positive lift configuration. And now I can see the transitions occurring about 1, 2, 3, 40% on the upper surface. You can see it right there. And on the lower surface, it's at 10, 20, 30, 40, 50, 65%. Let's just verify that in our data. If I come back here, we are here at 2 degrees. Let me zoom down the table here. 2 degrees. What did we say? 40% and 60%. There they are right there. So you can see how the transition points here. So this table is very useful. It basically contains, for a given Reynolds number, So for a given wing and flight conditions, flight density and velocity, there's your Reynolds number. As you vary the angle of attack, you can look at CL, total CD, pressure only CD, moment coefficient, and the point of transition on the top and lower surface. Very handy table. And we obviously use very small increments of 0.05 degrees, so there's a lot of numbers in here. You could paste this in Excel if you wanted, plot it externally or MATLAB or whatever you use, up to 20 degrees. The other nice thing you can do is if you want to know what angle of attack you need to hit a given lift coefficient. So let's say you had this airfoil and you wanted to know, you wanted the lift coefficient to be, say, 0.7 or 0.75. What angle of attack do I need to do that? Now here I can look at this list and I can see it's going to occur right about here, somewhere between this point and this point. So it should be about 4.65 degrees. These are the second column here is my lift coefficient. It should go to 0.75 between 4.6 and 4.7 degrees. Now let's just see if that's the case. So what I'm going to do is type CL 0.75 return. And now I'm going back here. What did we say it was going to be? 4.6. So 4.65, we guess it's 4.64 degrees is getting our exact CL. So you can put in an alpha and calculate everything, or you can put in a CL and calculate everything. So if you know the lift coefficient, which is probably more typical of what you would need to know, if you have a body of a given weight moving at a given airspeed, you could say, okay, this is the lift coefficient that I need in order to hold that thing in the air, and what alpha do I need to achieve that? So that's the opposite kind of thing. But we could always get at this data just by linearly interpolating, like you might in your thermodynamic tables. So that's about it. Let me look quickly to see if it's going to be easy to change the polar plot variables. Otherwise, I'll figure how to do that. I did like to see that. Let's see. I'm going to redo my polar plot with seq p. I'm going to do alpha minus 2 to 20 again, 0.05. Oh, I'm still in my thing. Okay, let me go back and let's see if I'm going to quit out of here, and we'll see if we come in, if we can see what the options might be. So again, I have this table here. I've saved it. It's 242112 screen cap. I saved it during that file history. So again, I restarted Xfoil. I'll quit here, and